Hello. In this second part of our video on buffer solutions, I'm going to do one more example of a calculation designed to create a buffer of specified pH and concentration, and finish up this section by talking about the concept of buffer capacity. So let's recap what we talked about in the first video. We learned how to calculate the pH of a buffer solution given the initial quantities of the acidic and basic components. That was our first problem. And also by using the volumes and concentrations of reactants provided in a partial neutralization reaction. That was our second sample problem. We then considered how to make a buffer solution of specified pH and concentration by combining calculated quantities of acidic and basic components. That was our third example problem, and that's what we finished the last video with. Now I'd like to talk about how to make a buffer solution of specified pH and concentration by combining calculated quantities of reactants in a partial neutralization reaction. Okay? So you'll see the second group of problems are kind of like the first. In the first, you are given the initial amounts of stuff from which you calculate the pH of the buffer solution. In the second group of examples, it's kind of the reverse. We specify the final pH and concentration, and we calculate how much stuff we need. Okay? So let's do this final problem. The question is, what mass of hydrochloric acid must be added to a specified volume of a specified concentration of the weak base dimethylamine in order to make a buffer of a pH of 11.00? Now, in this problem, we are adding hydrogen chloride to the solution of the weak acid. We're going to make the assumption that the volume change is negligible, namely that the final volume will be the same as the initial volume, which is 500 milliliters. Okay? Now, I also give you pKb for the weak base. So let's begin by writing out the equation for the weak base ionization, because we need to decide what equilibrium we're going to base our calculations on. So I'll write dimethylamine in water to form the dimethylammonium cation plus hydroxide. I'm going to simplify this by writing simply B plus H2O in equilibrium with BH plus OH minus, where we know B represents dimethylamine. So here's our little roadmap. We're going to use the pH and pKb, which is given, to calculate the desired concentration of the conjugate acid. That will give us the pH that we want. And then we're going to use stoichiometry to calculate the mass of hydrogen chloride needed to form that desired concentration of the conjugate acid. Okay, so let's begin. The limiting conditions or the boundary conditions we're given are as follows. The pH is 11.00. Because I'm given pKb, why don't we calculate pOH? That's simply 14.00 minus the pH, or 3.00. Let's begin by writing the equation for the reaction that we will employ to form the buffer. The reaction is going to involve the partial neutralization of dimethylamine. So that reaction is B plus H plus, where H plus represents hydrochloric acid, the strong acid, to form the conjugate acid, the dimethylammonium ion, which we're representing as BH plus. Okay? Our further boundary conditions, if you will, are that the sum of the concentrations of unreacted dimethylamine and the dimethylammonium ion we're forming is equal to 0.350 molar. That's the case because if you look at the equation right above it, we see that the total moles of dimethylamine and dimethylammonium must remain constant. And if the volume of the solution is not changing, then we are assuming that the sum of the concentrations will always be 0.350 molar, and that our volume is 500.0 milliliters. Okay? Well, ultimately, we need to find the concentration of the dimethylammonium ion, BH+. That will give us our desired pH. So let's jump to the Henderson-Hasselbalch equation. But now I'm going to use the basic form of the Henderson-Hasselbalch equation, and you can see from pretty straightforward derivation that that looks very similar to the acidic form. POH is equal to pKb plus the base 10 logarithm of the ratio of the concentration of the acidic component to the basic component. I'll I'll use that, I'll rearrange that to isolate the ratio of the conjugate acid to the base. That will be equal to 10 to the POH minus PKB, or 10 to the 3.00, which is our desired pH, minus 3.30, which is PKB, is 10 to the negative 0.30 equals 0.501. That means that my concentration of the conjugate acid, the dimethylammonium ion, is 0.501 times the concentration of dimethylamine equals 0.501 times the total concentration minus the concentration of BH+. Again, because we have the sum of the concentrations at the top, this is equal to 0.175 minus 0.501 times the concentration of the conjugate acid. 1.501 times the concentration of the conjugate acid is equal to 0.175, or the concentration of the dimethylammonium ion, the conjugate acid that will give me my desired pH, is 0.117 moles per liter. Okay? That's what we were shooting for. Now, I didn't ask for the concentrations of both, but we can go ahead and calculate that anyway. The concentration of remaining unreacted dimethylamine, the basic component, will be the total concentration minus the concentration of the acidic component that we produced, or 0.233 molar is the concentration there. Now, if you wanted to make sure that you did this correctly, you could always take these, plug them back into the Henderson-Hasselbalch equation, but you'll get the pH that we calculated. So now, to finish the problem, the mass of hydrochloric acid needed will be equal to 0.117 molar dimethylammonium ion times the total concentration times the mole ratio, 1 mole of HCl needed for every 1 mole of dimethylammonium ion formed, times the molar mass of hydrochloric acid, or my final mass equals 2.1 grams of HCl. So what we've done in this problem is a very practical thing. We started out by specifying the volume and pH of a buffer we're trying to make. We specified the weak base conjugate acid pair upon which it is formed. We specified the initial concentration of the basic component, and we calculated how much strong acid we have to add in order to form that particular buffer. So now let's finish up this section by talking about buffer capacity. So let's consider two acetic acid acetate buffers. In the first one, my concentration of acetic acid equals my concentration of acetate equals 1.00 molar. In the second one, the concentration of acetic acid equals the concentration of acetate equals 0.0100 molar, or a buffer in which the concentrations of the acidic component and the basic component are only 1/100th of the first. So my first question is, would there be any difference in the pH of these two buffers? Well, we know from either the Ka expression or the Henderson-Hasselbalch equation, pH equals pKa plus the base 10 logarithm of the ratio of the acetate concentration to the acetic acid concentration. Well, that suggests that if the concentrations, if the ratio of the concentrations of the basic component to the acidic component in the two buffers are the same, and pKa is the same, then the pHs should be the same as well. So I'm going to say no, there shouldn't be any difference in the pH. But here's the important question. Which buffer can absorb more external strong acid or strong base without a large change in pH? In other words, which one is going to be the more effective buffer? The one in which the concentrations of each are equal to 1.00 moles per liter, or the one in which the concentrations are only 1/100th of that? Well, you would predict, and you would be correct, that buffer A would be able to absorb more strong acid or strong base because the concentrations of the acidic component basic component are 100 times larger. There are simply more moles of acid and base in solution that can serve as a buffer by absorbing extraneous strong acid or strong base. So, to summarize, what determines the pH of a buffer solution made from a given acid-base conjugate pair? Well, again, I'm going to write out the Henderson-Hasselbalch equation. pH equals pKa plus the base 10 logarithm of the ratio of the basic component to the acidic component. Okay? So the two factors that determine the pH are basically shown right here. The identity of the acid or base determines the pKa, which is one of the factors that determines the pH. The other is the ratio of the concentrations. Those are the only two things that influence the pH of the buffer solution. But what determines the capacity of the buffer? What do we mean by the capacity of the buffer? Well, the capacity of the buffer is how much external strong acid or strong base you can add without drastic change in the pH. Well, what determines that pretty obviously is the actual concentrations of the acidic component and the basic component. Okay? Again, let's go back and look at the titration curve. Can we pop back to that? Oops, sorry. Yeah, okay. Here's our titration curve. And remember that if we are at the most effective buffer, we are in the buffer region. Okay? Let's imagine that we're at the center. So when we're in the buffer region and we start adding strong acid or strong base, this is what we do. When we add hydroxide, we move in this direction. When we add hydrogen ion, we move in this direction. As long as the concentrations of the acidic and base component are sufficient that you don't move out of the buffer region, then you still have an effective buffer. Okay? But if the concentrations are so low that adding strong acid or strong base moves you out of the buffer region, then you no longer have an effective buffer. Your buffer has been swamped. So that's all we have to say about buffers. See you in the next video.